Hello friends, I Professor Darshan Thakur from Terna Engineering College Dharamshi welcomes you on my YouTube channel for this subject head Control System Engineering. Friends, as far as our today's session is concerned, so we will try to discuss one of the most important parameter of this control system whose name is nothing but transfer function. So as you can see with the help of this graphical representation, one type of electrical network we do have with us. So apart from this electrical network, our objective is to what? We are supposed to determine the overall transfer function of that given electrical system, right? So as we know, this system is nothing but what? It is an arrangement of different physical elements. Those are connected in such a way that to attain a certain objective out of it, right? So such type of electrical network we are having with us. As far as this electrical network is concerned, so there are three basic parameters of this electrical network: resistor, inductor and capacitor, right? So such type of circuitry we do have with us. So here first of all we need to recall the basic definition of this transfer function basically. So as we know, transfer function is nothing but what? It is just similar to the gain of that amplifier circuitry. So the transfer function of this given electrical system is nothing but, it is very simple. It is the ratio of output of that system to the input of that system in case of S domain. But we need to understand that this transfer function is being defined under a zero initial condition. Means what? When the system or the overall system is at that rest condition, or more prominently we do can say that none of the energy component is being stored within each and every element of that system. So such type of condition can be called it as a zero initial condition. So transfer function, it is nothing but what? It is the ratio of output to the input is in terms of S domain. So here output is nothing but what? V of t. So its S domain representation will become what? V0 of S, and the S domain representation of that input is nothing but what? Vi of S. So we are interested to determine the output voltage in terms of S domain and the input voltage in terms of S domain basically. Okay friends, so after going through the basic definition of this transfer function, the next thing which we need to do is to determine the time domain expression for this input voltage as well as output voltage. So as you can see, there are two identical components. Obviously these two are connected in series form with each other. So by taking into account this such type of circumstances, here what we need to do, first of all we need to determine the time domain expression for this input voltage as well as the time domain expression for this output voltage, right? So in order to determine these input and output voltages, we need to admire one basic strategy which is used in case of this electrical engineering, in case of this series circuit. The name of that strategy is nothing but what? The Kirchhoff voltage law, or more prominently we do can call it as a KVL. By the virtue of this Kirchhoff voltage law, we need to determine the time domain expression for input as well as the time domain expression for output, because the S domain representation of this input and output voltages are required to determine the overall transfer function, right? So as we know, the Kirchhoff voltage law, that is nothing but what? Very simple strategy it is. The algebraic sum of all ohmic drops are always equated to 0, right? So when we apply this Kirchhoff voltage law to the input side as well as to the output side, so let us quickly go through this scenario. When we apply this Kirchhoff voltage law from this input side, so obviously this is the positive terminal and this is the negative terminal, right? First of all, that Kirchhoff voltage law is applied to this input section. So in this input section we are having one desired potential, that is nothing but what? Vi of t, right? The remaining two elements are concerned, those are nothing but, one is resistor and another is nothing but what? Capacitor. So according to that Ohm's law, we are very much aware of this thing ki the voltage drop across this resistor is nothing but what? Simply I into R, that we need to recall, right? Similarly, the ohmic drop across this capacitor is nothing but what? Obviously it is 1 over C integral of I of t into dt. these two statements we need to record, right? Because we need these two statements while defining the input voltage as well as output voltage, right? So when we apply this Kirchhoff voltage law to that input side, so the input current is nothing but what? Denoted by this statement, that is nothing but what? I of t. The current always flows from positive to the negative terminal, or more prominently we can say that it always flows to opposite direction as compared to the direction of electrons. The direction of current is always opposite to the direction of electrons, or it always flows from positive terminal to negative terminal. So the direction of current is here what? Is in clockwise direction. So carefully we need to follow this clockwise direction while applying that Kirchhoff voltage law. So accordingly, how this I of t current flow through this resistor which is connected in that horizontal arm? Obviously from its left hand side to the right hand side. So we need to mark the polarity. Similarly, how that current flows from this capacitor which is connected in that vertical arm, from top to bottom, right? So when we apply this Kirchhoff voltage law from this negative terminal, we are going from negative plate to the positive plate. So that's why the overall potential of this V of t is nothing but what? It will become positive, right? When we consider the ohmic drop across this resistor R, so at that time we are going from positive to the negative plate. That's why the overall polarity of this ohmic drop across that resistor is what? It is denoted by that negative sign. So obviously it will become R into I of t. That is nothing but what? The ohmic drop across that resistor. Similarly, the ohmic drop across that capacitor, the time domain expression is nothing but what? 1 over c integral of I of t into dt, right? Here we are going from top to bottom side as it is connected in that vertical arm. So obviously the ohmic drop across that capacitor will be negative. So minus 1 over c into integral of I of t into dt. So this is how this statement will look like. When we rearrange this term, so we will come to know V of t equals to what? R into I of t plus 1 over c into integral of I of t into dt, right? So this will become the time domain expression for input voltage, right? We want this input voltage is in terms of S domain. So when we apply the Laplace transform to this existing statement, it will become what? Vi of s into R times of I of s plus 1 over c, as we are having the integral sign, so the Laplace variable will be what? It will become 1 over c into s followed by I of s, right? So this is how this equation number 1 become, right? In same manner, when we apply the Kirchhoff voltage law to that output side, right? So similarly, such type of expression we are getting to that output side. We are having one potential, that is nothing but what? V0 of t, and the output is obtained across this capacitor C, right? How we are mapping this capacitor? When we apply the Kirchhoff voltage law from that output side, we need to follow these two polarities. We are going from top to bottom, right? So V0 of t minus the ohmic drop across that capacitor, so it will become V0 of t minus 1 over c into I of t into dt. So finally V0 of t equals to what? It is 1 over c integral of I of t into dt, right? And when we apply the Laplace transform, so it will become what? V naught of s equals to, again the Laplace variable will be 1 over s, so 1 over c into s followed by I of s. That can be called as the equation number 2, right? Now the transfer function is nothing but what? It is the ratio of output voltage to the input voltage in terms of S domain, right? So here when we equate these two equations to determine its overall transfer function, so it will become what? Initially we need to consider the equation number 2. It is 1 over cs into I of s. Its denominator will be what? The equation number 1, that is nothing but what? Here while considering this denominator, a few mathematical simplifications we need to look out. Here this I of s is common term, so the remaining its coefficient will be what? R plus 1 over cs into I of s. So finally this I of s will get cancelled, again it will get cross multiplied. So answer will be what? It is 1 over RCS plus 1. That is nothing but what? The term which is written within this rectangular box is nothing but the overall transfer function of this electrical system. So friends, in this way we had tabulated the transfer function of this given electrical network, which consists of two identical elements, resistor and capacitor. So by the virtue of this Kirchhoff voltage law, we can determine the transfer function of any kind of electrical network which can have these three identical elements like resistor, inductor and capacitor. If we are having an inductor into that circuitry, so to that inductor again we need to recall the time domain expression or the ohmic drop, how to represent the voltage across that inductor. So it is denoted by this term Vc equals to what, L into di by dt, that we need to consider when an identical inductor is connected into that circuitry, and obviously its S domain representation will become what, Vc equals to, as we are having the differentiation sign, it is a first order differentiation, so the Laplace variable will be S, Ls into I of S. So in this way that term is to be represented whenever we are having inductor which is connected into that circuitry. So in this way the overall transfer function is to be tabulated. Thank you.